Hello everybody, and welcome to Theorem 1.2 on page 12. This is going to be our last theorem of section 1.2, and we're going to take this and try to prove the first two parts of this theorem. Let's first kind of read through it together here. So it's saying that in any vector space V, the following three statements are true. The first one says that if we take the scalar 0 and multiply it by the vector x, we get the 0 vector for any vector in our space. Part B says if we take the scalar negative a times x, that's going to be the same as the negative of the vector a times x, which is a times the vector negative x. Okay, and then finally, statement C says that if we take any scalar a and multiply by the 0 vector, we should get the 0 vector back again. Okay, you might look at this theorem again and say these statements really seem pretty obvious. Why should we have to prove them? Well, again, remember that we're trying to prove that these statements are true in every single vector space. Our vectors could be really bizarre, very abstract objects. And so to really be sure that these statements are true in every vector space, we need to write a careful proof using our definitions and theorems that we have up to this point. Okay, so let's see if we can write a proof of the first two parts of this, starting with part A. Okay, and the argument for part A is not terribly long, but it's a little bit tricky. Whoever thought of this argument must have really had to fiddle with equations a while to kind of come upon this. So here's what we're going to do. We're going to take the 0 vector and add it to the scalar 0 times x. Okay, and then notice that by definition of the 0 vector, that should be 0x. Okay, so if you want a reason for that first equality, we're using VS3. Okay, just the definition of the 0 vector, basically. Okay, and then that's the same as 0 plus 0 times x, because the scalar 0 plus itself is just going to give us 0. So in other words, this and this are the same. Okay, and then we can use VS8 to expand that into 0x plus 0x. Okay, but take a look at where we started and where we stopped. So we have this at the beginning and this at the end, and so we can use the cancellation property to get rid of those 0x's that we have there. Okay, and so therefore 0x is equal to the 0 vector by the theorem that we just proved in the last video, Theorem 1.1. That's the one that says that we can cancel the 0x that we see there. Okay, now let's, just for the sake of your notes here, I'd like to clear a little bit of clutter away here. Okay, so 0x Okay, there we go. All right, so that was kind of a short proof for A. Now let's see if we can prove B. That's a little bit more involved. And this is one of those proofs where it might be difficult even to say, where do we begin on a proof like that? How do we show that these three things are equal to each other? Well, it kind of comes down to really carefully thinking about what each of those things represents. Okay, so let's try to put into words where we're going here first. So in words, okay, we want to show that negative a times x and a times negative x are both equivalent to the vector that was in the middle minus a times x. And that negative of a times x in words, that's the additive inverse of the vector ax. That's kind of the key. Okay, so how do we do that, or how could we do that? Well, first thing we'll notice is what happens if you take negative a times x and add it to a times x. Okay, let's just do the arithmetic, see what happens here, and then we can talk about the meaning of it. So we're going to use part A actually and a couple of properties of vector spaces at the same time. So the first thing we could do is to group the minus A and the A together. You can look back at our list of vector space properties and maybe find the one that lets us do that. Then the scalar negative A plus the scalar A is 0. And then by part A, we proved that 0 times x is the 0 vector. Okay, so what does this say? Well, if you look back at where we started, we took the vector negative A times x and added it to A times x, and we got the 0 vector. That means that this vector that we started with here has to be the additive inverse of AX. It's the vector that we needed to add AX to get back to the 0 vector. Okay, so what we can say, let's put that into words. Negative A times x is the additive inverse of AX. And that means by definition, we have shown that negative A times x is the negative of the vector A times x. Okay, I'm going to give that equation a number because we're going to use it a couple of times as we continue with the proof here. Okay, and in addition, let's make another couple of observations here. Okay, let's see how we're doing with space. It looks like we're okay. Okay, if we start with A times negative x, okay, we can do a couple of things with that. First, I claim that that's equal to A times the scalar negative 1 times x. Now, where did that come from? Well, basically, we just used formula 1 up here with A equals 1. Okay, if you substitute A equals 1 up here in formula 1, that tells you that these two pieces that I'm underlining have to be the same. Okay, and then we can use a couple of other vector space properties. Okay, so this is the same as negative 1A times x. That's by BS6. Okay, and then negative 1 times A. Those are both just scalars, so we're going to get negative AX. So that's ordinary scalar, let's say it this way, multiplication of scalars. Okay, but then negative A times x, we showed up here in number 1 that that's the negative of AX. Okay, so by 1 again. All right, well, this is kind of a tangle of things that we've shown. Let's see if we can sort through it and just make a couple of observations. So basically, we did two things. We showed that this vector negative AX, that appears in two places. And notice that we demonstrated that it's equal to negative AX and also to A times negative x. Because both of those are true, we've really shown that all three of these things up here are equal to each other. Okay, so let's put that into words and then we're done. So since we showed that negative negative AX and A times negative x are both equal to the negative of AX, okay, the result follows. Okay, it tells us that all three of those vectors are equal. Okay, and there's our proof of B, and if you're interested, you can look at the textbook and see a proof for part C.